we found G sub 1 seeded false and X1 original false. Then, assuming that the fraction of the false found of the seeded false is equal to the fraction of the false of the original false, we get an estimate of the original number of false. Okay, what do you think? Do you think it seems like a good method?
It actually depends on the type of the seeded faults that we introduce in the software, because if these faults are very close from the actual ones, the original ones, then our estimation will be accurate. But they are far from that, then our estimation is not accurate.
That is true. So yeah, so typically when you seed faults, faults are seeded by using relatively simple operations. So for example, you will change some operators.
Rotation.
So you will change some operations, you will change some minor things. And whereas the faults that are hard to test, they often depend on some kind of flaw in the high-level logic. So it is very hard to seed faults with very low detectability. So if you are considering a situation when you already have done some testing and the defect density is already reasonably low and you want to estimate the number of faults, then in actual practice, so this is the estimate. Actually, the false X includes hard to test faults. And thus, in a typical situation, the likely thing is that these faults are easier to test, and hence you are going to find a greater portion of the seeded faults rather than the portion of, so this is the one, portion of the original faults. So this is the likely situation. Hence, X is likely to be greater than the estimate. Now remember, the detectability of faults can range over a very wide spectrum. They can differ by several orders of magnitude. So if you have a piece of software, maybe you have a million different combinations. Some of the faults would be tested by almost all of them. Some of the faults may be tested by only one or two combinations. So they could be different by orders of several orders of magnitude. Any questions? So here is the implication that you have to be very careful when you interpret the result of seeded faults. Any questions? questions or comments?
So we do this because we want to, when we estimate the number of original faults, that will help us in the testing and test coverage, right? This is the purpose of that. So if we know like what is the estimated actual number of faults, then when we do the test coverage, we'll stop at a certain point when we know like we covered 70% or something like that.
Right. Yeah, but of course, when you, for comparison, it is valid.
Yeah.
So if you have a method that catches more of the seeded faults,
Yeah.
then that is evidently a better testing approach.
Mm-hmm.
That is true. Okay, so that is our discussion on random testing. And incidentally, the results on random testing are probably also generally applicable when testing is not random. The difference would be that in case of random testing, here's coverage, here's time for the number of vectors applied, and here is coverage. And if it is random testing, coverage may grow like this. And if it is a scheme that is more efficient than random testing, and it is not easy to get a scheme that is more efficient than random testing. Random testing is actually a pretty good testing approach, but let us assume that you can get a scheme that is better than random testing. What will happen is that things could be like this. So eventually they will start converging. We proposed a scheme called anti-random testing. In anti-random testing, maybe I will talk about that sometime. That is an idea that we struggled with for quite a while. So the idea is that each test applied is as different as possible from all the tests applied before. And the idea is that this way, every test has the best possibility of detecting additional faults. Mm-hmm. And then so at first we couldn't figure out how to generate these anti-random sequences without doing an exhaustive comparison every time. Mm-hmm. But then we figured out some kind of method, which we think it may be an algorithm, but we haven't been able to prove that it is an algorithm. And then we forgot about it, but then there was a master student, and she got interested in it, and she wrote a program to implement that procedure. So there's a way to generate anti-random tests, and we applied it to software and to hardware, and we got really good results. So if this is random testing, then this is what you will get with anti-random testing. And after we did this work, there were some other people, they came up with some modifications of the technique we proposed. So there are some variations of our anti-random testing. But maybe I will talk about that sometime. Okay. So next let us come to, okay, finally, let's talk about software. Actually, we were already talking about software. So this part, test detectability profile idea is actually applicable to both. It is applicable to hardware. It has been used in hardware, and is also applicable to software. And now let's talk about software reliability. So, now typically in this class, I have a combination of people from electrical engineering and computer science. So this time we have more people from electrical engineering than computer science, but sometimes it's the opposite.
It's usually the opposite.
So yeah, usually a lot more computer science students. And but I think many of the things are applicable to both. Now here we are going to be talking about software mostly. And now let's consider the field of software reliability versus hardware reliability. So here let me make an argument for studying a systematic software reliability engineering. So what we are going to study can be termed software reliability engineering. Now we have these terms. We have things like craft. Like some people, they enjoy working with wood. They enjoy woodcraft. And craft is basically sort of intuitive and incremental refinement. You learn more and you get better. And then you have the science. Now science answers the question why. Right?
Sometimes.
So you study physics, chemistry, and you study physics and you will know why this object, when it drops, it will hit the ground at a certain speed. So it answers the question why. And then of course then there's engineering. And engineers are interested in how. Okay, so we know that it is going to strike the ground, but how can we make something using this principle? And that satisfies some requirements. So basically engineering is how to get done what we want. How to get what we want. So in that sense, software reliability engineering is engineering because it is about how do we get what we want, and typically we want a certain degree of assurance that the software will work correctly. And notice that here you need to do a few things. You need to approximate. Okay, you cannot do engineering without approximation, right? So in ECE, when you do transistor level modeling and you use some model and it includes approximation, it turns out a fairly good approximation. And but if you wanted to consider all the possibilities, you will never finish anything. So you always have to do some approximation, very important. So you need to approximate and you need to integrate ideas. You need to combine the ideas so that you can do what you want. And you need to evaluate your approaches. So for example, you want to find out the best way to test some specific type of software. You need to evaluate a proposed approach to see if it indeed works the way you think it does. Now let's talk about software versus hardware in terms of reliability. Now people in hardware, they are comfortable with reliability ideas. And let me give you a quick historical background. In hardware, reliability has been around for a much longer time. There are a lot more papers on hardware reliability. Now, you may have heard that when computers were built after using tubes, then the MTTF, mean time to failure, for the system was comparable to some of the computation times, which was a problem because you finish a computation and check and make sure that tubes are still okay. And then, so they start thinking about the failure rate models. So there was a, in 1956, RCA, that used to be a big company. I don't know if you guys, has anyone heard about RCA? It used to be a big company, Radio Corporation of America. And so they came up with TR 1100. So it's a failure rate model. And then in 1959, military came out with the military handbook, HDBK 217A, for failure rate estimation.